Okay, so we're on to our second lecture on power series. I'll do some examples here. We're still talking about power series expanded about zero. In our next lecture, we'll talk about power series expanded around other points. This is for a lecture made for my Calc II class, and we're about 3/4 of the way through. So if you're not sitting in on a Calc II class right now, you may not follow this right now. So we had just defined power series in our last lecture, and we realized that these are functions of x. So they're series that you can change the value of x for which you're working with, and the domain of this function is going to be the values of x for which it converges. So what we're doing right now is we're looking at ways, we're looking for the domain of this function. Okay, so in our last example, in our last lecture, we saw a couple of situations where we had geometric series that we could talk about, and we could find the domain by the rule for geometric series. And we had one example that was not a geometric series, and we had to do some work to figure out what the domain was for that. We used the ratio test. Generally speaking, when it's not a geometric series, the ratio test is a pretty good bet, at least to get started and end up finding the bounds on the set on which it converges. And if it's sometimes the root test. We'll do at least one example where the root test might be useful too. Okay, but let's look here. Here you notice this is not a geometric series because of this n here. If that n wasn't there, I could factor a 2 out of here and I'd have 2x over 3 raised to the n. I'd have a geometric series, but with that n, I don't have one. So we want to figure out the set of x for which this converges. I'm going to start with the ratio test. So the ratio test is saying that's going to converge absolutely if the limit of the n plus first term over the nth term is less than 1. So let's look at that limit. So we're looking at the limit as n goes to infinity of the absolute value of the n plus first term. So that's n plus 1. 2 to the n plus 1 plus 1. That's n plus 2, right? X to the n plus 1 over 3 to the n plus 1, so that's the n plus first term, and then over the nth term, so that's n, 2 to the n plus 1, x to the n over 3 to the n. And let's make those absolute values a little longer. Okay, so we're looking at this limit. Of course, we can invert the denominator and multiply. Again, the only factors here that might be negative are the x's, and so we can simplify and put the absolute values with the x's. And so that's the limit as n goes to infinity. What do we have? N plus 1, 2 to the n plus 2, 3 to the n, absolute value of x to the n plus 1, over n, 2 to the n plus 1, 3 to the n plus 1, absolute value of x to the n. And now a few things cancel here, so this is going to be the limit as n goes to infinity of, well, the 2 to the n plus 2 divided by 2 to the n plus 1 is going to just be 2, right? So I'm going to have n plus 1 over n here times 2. 3 to the n over 3 to the n plus 1 is 1/3. And then x, absolute x to the n plus 1 over absolute value x to the n is just absolute value of x. So again, n plus 1 over n is a rational function. Degree of the numerator and denominator are both 1. So that limit is just the ratio of the leading coefficients, which is 1. And then 2/3 times absolute value x is just constant with respect to n, so that doesn't change. So this goes to 1 times 2/3 absolute value x. Okay, so that limit's going to be 2/3 absolute value x. So what does that tell us? Let's see. That means if, let's change the color here. So if 2/3 absolute value x is less than 1, that tells us it converges absolutely, right? So those points x for which this is true are definitely in the domain. If 2/3 absolute value x is bigger than 1, that means it diverges. So those points are definitely not in the domain. So let's just rewrite what these points are. This is the same as absolute value x less than 3/2, right? Or the same as negative 3/2 less than x less than 3/2. Okay, so it converges absolutely on the open interval from negative 3/2 to 3/2. It diverges if x is bigger than 3/2 or x is less than negative 3/2, right? So the only issue now is we don't know what's happening at those endpoints. So the domain of this function is one of 4 things now. It's going to be either the open interval that we just wrote, negative 3/2 to 3/2, the closed interval, including both endpoints, negative 3/2 to 3/2, or one of the half open intervals, negative 3/2 including negative 3/2 but not 3/2, or vice versa, including, sorry, that should be open there, including 3/2 but not negative 3/2. Okay, so we're almost done. Now we've got to test the endpoints and decide which it is. So let's look at x equals negative 3/2. At x equals negative 3/2, my series is the sum. Now remember, when we're determining if it converges or diverges, where we start at doesn't matter. It only matters if you tell what it converges or diverges to. Okay, so that's plugging in negative 3/2 for x, right? And we can simplify this. This is going to be the sum n equals 1 to infinity of, well, that's going to be negative 1 to the n, 3 to the n over 2 to the n. Well, we may as well write that, right? And that simplifies then to the sum n equals 1 to infinity of negative 1. So it looks like, okay, I get left with the 2 in the numerator and the 3 to the n's cancel. So I get 2 times negative 1 to the n times n, and that's going to what? Diverge. Why is that? That's the divergence test. Terms don't go to 0, right? Terms don't go to 0. Okay, so right off the bat we know, so that's at negative 3/2, so we know that's not it and that's not it, so it's one of these other two. Okay, so let's try x equals 3/2. So that's going to be n equals 1 to infinity of n times 2 to the n plus 1, 3/2 to the n over 3 to the n. And when we multiply, we're going to end up with 2n there, right? When we cancel things. And again, that diverges as well, because the terms don't go to 0. That's the divergence test. So neither endpoint is included in this example. So all 3 of those, this is the domain. So the domain of this function is the open interval from negative 3/2 to 3/2. Okay, so let's erase this and do one more. Okay, so this one I have up here, again, it's not a geometric series because of that n to the n. It's not a constant raised to the n. The index of summation is n, and it's n raised to the n, and that's an issue. This is one we could use a ratio test on, but the root test might be a little bit easier. Again, what are we looking for here? We're looking for the domain of this function. That means the set of x values for which this function converges. And let's go over here. I'm going to try the root test for this one. And the reason I'm going to try the root test is because everything was raised to the nth power, but it's not a geometric series. So I'm going to look at the limit as n goes to infinity of the nth root of the nth term, the absolute value of the nth term, so that's going to leave the absolute value x because everything else is positive. And that nth root, of course, that's raising it to the 1 over nth power, and when you multiply and divide numbers, you just can distribute the powers over that. So that's going to be 2 to the n to the 1 over n, which is just 2. Absolute x to the n to the 1 over n, which is absolute x. N to the n to the 1 over n, which is n. So now as that goes to infinity, this is going to equal 0, right? And that's regardless of what x is. For any fixed value of x, that's going to equal 0, which is less than 1. So the series converges absolutely for all x. Okay, that means the domain is going to be all of R. The domain is all of R, or you could write that as negative infinity to infinity. Let's do one more example before we go to the next lecture, where we're going to be talking about the radius and interval of convergence. So let's just try one more example. N equals 0 to infinity of n factorial x to the n. Okay, so, well, I'm going to try the ratio test on that. It's certainly not, not root test, but ratio test. It's certainly not a geometric series, and it's not a good root test one, so we'll try the ratio test. So we're looking at the limit as n goes to infinity of absolute value of the n plus first term, n plus 1 factorial, x to the n plus 1 over n factorial, x to the n. And of course the absolute values just go on the x's because everything else is positive. N factorial divided by n is just n plus 1 factorial divided by n factorial is just going to be n plus 1. Absolute x to the n plus 1 divided by absolute x to the n is just that. And notice this limit, well, there's something to be careful of. There's one x for which this converges to something finite. If x equals 0, each of these terms is 0, right? So if x equals 0, this goes to 0 if x equals 0, because that's going to 0 out before you even evaluate the limit. However, if x is not 0, if it's some other fixed number, this is just going to be infinity, which of course is bigger than 1. So by the ratio test, it diverges for all x not equal to 0. Diverges for all x not equal to 0, because that's bigger than 1. Infinity is bigger than 1. But does it converge at 0? Yeah, notice, well, by the ratio test, it converges at 0. However, you can tell easily it converges at 0, because if you plug x equals 0 in, you only end up with the first term, which is 1. It converges at 1 at x equals 0. So the domain of this function is just singleton 0. And that's it. Okay, so next lecture we're going to talk about expanding around something besides 0, and then the following lecture we're going to be talking about the radius and interval of convergence for these things. We can actually talk about the domain of convergence much more nicely. So this is a good place to stop.